Good day everyone. I hope you are doing great from wherever you are watching this video. This is going to be a quick tutorial on how to use Hydrus to simulate a drying experiment in the laboratory that has a time variable condition. Imagine you want to calibrate an experiment you've carried out in the lab using numerical methods, a numerical model. So this is an example of what we'll be simulating. Imagine Professor Curie carried out a drying experiment in the laboratory, and the experiment is carried out on a silty sand in a sand column of 1 feet diameter and 1 meter height. For us to be able to do this, we need the soil water characteristics curve and the unsaturated hydraulic conductivity functions of the soil. And it's the silty sand SM and ML. So we are going to use the SM properties in this table. Also, we need to know the time variable conditions for the number of days we want to simulate. In this case, we have been given for days 0 to 100 and days 101 to 200, just for you to have a better understanding of what we want to simulate. So imagine this is the sand column. It's 1 meter high and it's 1 feet in diameter. So at the bottom boundary, the experiment is sealed. That means it is constant over time. But at the top boundary, it is open to the atmosphere, which means the evapotranspiration ET varies with time and the precipitation P varies with time. So let's go to Hydrus to simulate this experiment. So when you open your Hydrus, you can click File and click New. So it's going to ask you for the name. Just say experiment 1 and click Next. So it's asking us the domain we want to simulate our experiment. We'll be simulating it in a 2D axisymmetry. So we're going to change our unit to meter, and for the X, which is the diameter, we are going to use 0.15 because we are simulating axisymmetry. If you check our question, the diameter is 1 feet. An equivalent of 1 feet in meter is about 0.3, but we'll be using the radius. So we'll be using the radius, we are cutting it in an asymmetry, so it's going to be 0.15 meter. So 0.15 meter and a height of 1 meter. So check this and check this, then click next. So what are we simulating? We are simulating water flow, then you click next. And how many days is going to be 200 days, and we're having a time variable condition. So we're going to pick 200 here just for a reason which I'm going to explain later on. And in this case, for our outputs, we want it to be every day. So 200, click update, then you click next. You don't need to change anything here. If you want to know more about this, you can watch my previous video. And in this case, what hydraulic model do we want to use? We'll be using Van Getjen Mollem 1980. And click next. So what material are we simulating? We are simulating SMML. So that's the material we are simulating, SMML. SMML. And this is the saturated water content. This is the alpha, this is the n. So we need to input these parameters. So for theta R, saturated water content, okay, theta S 0.35, 0.35. Residual water content, theta R, residual water content 0.02, 0.02, 0.02, and the alpha. In our case, we are given alpha in centimeter raised to power minus 1. So, and in Hydrus, if you check it, is in meter raised to power minus 1. So we need to convert it. So it's going to be 1.2, and our n is 1.123, 1.123, and our saturated hydraulic conductivity is in meter per day. So we are given from the question to be in centimeter per second. So we convert it to meter per day, which is 7.78 E minus 3. So 7.78 E minus 3. So, and this is the tortuosity. I mean, I is a parameter that relates to the tortuosity, the pore connectivity. We don't need to change it. I'm going to leave it at 0.5. If you are working on a calibration, those are the parameters that you can be changing if you want to calibrate a particular model. But in this case, we are going to leave it at 0.5. Then you click next. So it's now asking you for the precipitation and the evaporation on every day. So in our case, since we are given the question that for a 0 to 100 and from 101 to 200, so for the first thing that is asking us in Hydrus is the precipitation. So from a 0 to the 100, the precipitation is 0, but the evapotranspiration is 0.01 meter per day. So I've created it from 1 to 100 just for it to be easy for me to cut and paste. So the evapotranspiration, and for day 101 to 200, for day 101 to 200, the precipitation is 1 centimeter per day. So I've also converted it because in Hydrus it is in meter per day. So it's going to be 0.01 and others is 0. It's asking for transpiration here. You can just leave it the way it is here. This is talking about the potential transpiration. If you want to know more about it, you can just click help and you'll be able to read more about the potential transpiration. So in this case, we're going to leave it as 0.04 and we are going to click next. So this is the meshing parameter. It's okay like this. We click next. So it's saying the next task is to define the transport mode in graphical mode. We click OK. So we are going to use polyline. Then we are going to draw the boundary of the column we want to simulate. Then you click apply. You can click escape. Then you right click on this and delete the point. The next thing is to add surface to this. So you can come to your curve, click on the polyline. It's going to highlight it in yellow. Then you're going to click on planar surface generate. It's going to tell you that one or more surface were created successfully. Then you click OK. The next thing is to mesh. So you can come to the right panel here and click on mesh. So you need to generate our mesh. After generating it, you click next and it's going to tell you the next thing you need to do. Define domain properties, initial conditions, and define boundary. So the domain properties, where they have it as our SMML. The another thing you can add is the observatory nodes. So you can add some observatory nodes if you want to do some study. So insert observatory nodes. So you can add one there and you can add one here. Then the next thing to do is to define your initial boundary conditions. Our initial boundary conditions, since from the question it is initially saturated, you're going to use linear distribution with depth, and we're going to make this minus 0.01, and you're going to leave this at 0. You're going to apply, then click OK. The next thing is for us to set our boundary condition. So to set our boundary condition, this is going to be no flux, and that's the white we are seeing. And at the bottom too, it's going to be no flux. But at the top, we're going to be having atmospheric boundary condition. And for us to see this in a more better way, simulating like the right dimension of our column, you can go down to view stretching, and you can say no stretching and apply, then OK. So it's giving you like a right, it's drawing it to scale. I think that's the best way to say it now. So the next thing, you can run your model, calculate, click yes. So it's running. It's done running, just click enter. So for you to access your result, just come here, cumulative flux. And from the question, what we are interested in is for the first 0 to 100 days, the water evaporated. So you can go to cumulative evaporation. So for the first 100 days, the cumulative evaporation is about 0.00185 centimeter cube. And the second thing from the question is from 101 to 200 days, what is the cumulative surface runoff? So to get that too, we just need to change here and check the cumulative surface runoff. And that's how to simulate this question. What I mentioned I was going to explain in the beginning is if you check the project information, click next where you inputted the time variable boundary and it's asking you for the number of time variable records. I use 200 because in case if you want to simulate a time variable which is not constant even within the first 100 days like this question, this is the best way to simulate it. Just cut and paste the variable conditions for every day. But in this particular question where you have a case like this, you can just use 2. Then you're going to input your variable condition from 0 to 100 and from 101 to 200. And lastly, we added observation points. So if you want to check what is going on within the experiment, you can use your observation points. So these are the 2 observation points I created. I can check for the water content, and I can know how the water content is increasing or decreasing with time. So I can add legend here. So anyone is telling me observation node 1 and this is observation node 2. So however, or the time you put your wherever you put your observation nodes, you can use it to investigate what is happening at a particular location. So this is going to be all. Thank you for watching. If there is any comment, you can let me know below.